Okay, so right now, this time I will start from a new unit that was nonlinear analysis. So first, we're beginning with something that everybody is familiar with incremental method and the restoring force based method. So the marks will be a little bit different with multiple sense lectures. So I'll introduce them from the beginning. So here we have the equations of motions, but here remember this is x2 dot, which is acceleration of the current step, n+1 step. This is a vector v of the n+1 step. This is d, displacement of the n+1 status. And we have ground motion, ag, which rate from the file, ag n+1. Remember that when we do the calculation, we all use meters, second, Newton-based unit, okay? And we have the linear acceleration method that tells us that Vn+1 equals Vn+1 divided 2 bracket An+1 delta t, which are showing the velocity will be changed with the average of this step, last step's acceleration and next step's acceleration. You change with the gradient of the average of these two steps acceleration. And dn will be increased from based on the last step, and you will get the influence of their last step's velocity, get influence of last step's acceleration, and influence of next steps, this steps acceleration change. This is the third An+1, right? Then instead of using D, we use A to calculate. So we put these two equations. We put these two equations, Vn+1, Dn+1, there's two equations. Let me see, where is my, okay. We put these two equations to here and here. So we get this one. This one is not changing, right? So this one changes to the equations we get here. And this one we get the equations we change from here. Okay. So that this one is not changing. Then we can get some result. We summarize everything about the green one, about the N+1, summary every one, M, okay? This one, 1 divided by 2, 30, and C here, right? And beta, and K, and delta T square here. Okay, summarize everything about N+1. And then we throw everything back to the other side of the equation. Here I use the marks of Agn+1, which before in the multiple sense slide, I think is minus Agn+1. That is a simple way to express acceleration. So it's depending on you have a accelerator on the ground, right? So minus or plus is all in the direction of the record, right? It will not influence the amplitude of the result. So all in the so we are right now considering when earthquake shaking to this direction, right? Then because of inertial force, structure will define deformation like this, right? Because the ground shake to this side, so we shake to the other, deformate the other. So the deformation of the building structure are different with the ground. So that's all. But the result will be the same. Okay. So let's throw everything back here. Okay. Then we summarize the equation I showed you before, right? So N+1 actually you can give simply of F hat divided by M hat, which M hat is something about N+1 And F hat is actually what else? You throw it away to another side of the equation. Okay. And AV and AA here is just a simple way to let you don't need to write a very long constant, right? Remember here, M hat are all using constant value. They are not changing with the steps. Okay, they don't have A, they don't have V, they don't have D. The mass don't change, damping don't change, and K don't change. Beta, delta D, they don't change. This is all constants, right? So in the programming, once we calculate it, we don't need to calculate it every time. So this is constant. We like constant, so we don't need to calculate it every time. AV, AA, the same. They are all constant. They don't change with steps. Okay. So this is just a very fast review of what you have been known until here, right? Very easy for you. Let's try something new, okay? Try something new. But I think Matsumoto already said it in his lecture. So you have Vn plus one step equation here, Vn plus one equation here, and n step equation here, right? Both of them will fit with the equation of motion. They all follow the rule of equation of motions, right? So both Newton and Isaac Newton is correct, so that they are all in any time they will follow the rule. Okay. So we just divide each other, the two equations. This equation divide this equation, okay, to subtraction of them. So this first part becomes n plus 1 minus an, and the second part becomes this one, the third part becomes this one, this part becomes this one. And then you can get the incremental shape of the equation here. Okay, so you don't need to memory this, so they will be kind of boring. But if you try to memory it, maybe my explanation is too fast. So if so, I will later have some small tests for you so you can catch up. Okay. So you can get, this is very easy to understand, that you're just changing everything with the delta here. You're changing everything with the delta here. Acceleration, velocity, displacement, ground motion, all of them just with the delta here, right? Nothing magic. So delta V, what is delta Vm? We get it before, right? We just don't need the part of Vm part. We just need to know the changing part will be fine. And delta Dm part, I jumped a little bit about these equations, but you should understand that we before we use am plus half am plus let me make some supplement here, but make sure that somebody can see this. So before we know that very short one. Let me sure my camera is here is okay. Hope this side will be fine. Okay. So Vn plus 1 goes to Vn plus half. Sorry, too long time, no face-to-face lecture, so I'm a little bit rusty. So please give me a little bit of time. So n plus an plus 1, the t, right? So we just get Vn plus half an plus delta t plus half n plus 1 delta t. Right? So we get Vn plus half an plus half an minus half an delta t, sorry, delta t plus half an plus 1 delta t. So we just sum 1 and deduct 1. Okay. So we sum them together, then we get Vn plus an delta t plus half an plus 1 minus an delta t, which is the equation we see here. Equation we can see here. This one. See this one. So that delta Vn plus 1 equals to Vn plus 1 minus Vn. Just ignore this one. Oh, sorry. You cannot see because of this one. Better? Then you can get an delta t plus half. So that is the reason that I like incremental method, that the equation becomes shorter if you only consider incremental. Okay. So the same operation can be done for delta dn that you can get it from equation of the last one. Get the last equation here. Okay. So let's do a little bit expansion about the equation. Okay. So we put delta Vn plus 1 and delta d n plus 1 to the equations of motion in the incremental method, that it can be right like this part. So this part is the delta Vn. So this part is delta d n plus 1. N plus 1. Right now, all in delta an plus 1 is unknown value. So an, vn, dn were already calculated in the last step. It's already known value. So this part, only this part is unknown value. So the difficult of this part is only to derive the equations. So if you know the result of the equations, so it's super easy. So you summarize everything about delta n plus 1 to this equation, which is same with m hat we did before, and then throw everything to the other side of the equation. You'll realize that the residual things are far more shorter than we've done before, right? So summary is like this: collecting everything about an here, collecting everything about an here, right? And lefting only the vn here. So an vn is very step changing, but these two are constant. These are all constants, right? You just subject to the constant, and you get delta vn plus 1. So we're using a very simple and shorter and efficient way to express the incremental method here. Which is delta an plus 1 equals delta f hat divided by delta m hat. Delta m hat is, you can actually, the correct expression is m hat minus 1, the inverse matrix of m hat. What inside m hat is just a equation of, oh, sorry, this is for single degree freedom, so no problem. Okay, this is just the value, So no need to panic. Okay, so m plus delta 1 divided 2 c delta t and k beta delta t squared. So in the unit, they will all becomes mass. In unit, they all becomes mass. Okay. And then delta f hat is what we threw away to the other side of the equation, and with incremental of the external force which is m multiple the acceleration of the ground motion. And with AV and AA. So you'll need to what you need to do, really need to do is to derive these equations by hand later. Okay, so put back delta A here, n plus 1, Vn plus 1, and Dn plus 1. You can get their response, whole set of the response here. Okay, then we well, do another thing that we try using force space method. Using force space method here, instead of using K and D, we use F here. Instead of using K and D, we're using F here, which is this part. Okay. Before it was K multiple Dn plus 1. Right now we're using Fn plus 1, which is a spring force. Whenever it is linear or nonlinear. Okay, you see this here is the changes, right? Here's the changes. So for these equations that the K do not need to be constant. They can be changed. They can be changed step by step. Once you know what is Fn plus 1, then you can show the equations. Okay. So we pretend that Fn plus 1, we already know. Okay, we pretend Fn plus 1 is already known by some magic reason. We don't know. Okay. And so Vn plus 1 still here, and you don't need Dn plus 1 anyway. You just Vn plus 1 and substitute to Vn plus 1 into the equation, then you can get this one. See, the equation becomes even shorter, right? No hard equations. Right now, the equations even becomes more harder that M hard becomes only shorter because they losing the power of swiftness only in the right side of the force. But you see, the right side have a blue one, Fn plus 1, which you need to be careful about. Okay, this is a magic number here right now. It's magic inside here. Okay, so in the beginning, once we know the magic result of Fn plus 1, once we know this magic number of Fn plus 1, then we can solve the equations. We can get n plus 1 and get, of course, acceleration and velocity and displacement also. But the problem is that how we can know the Fn plus 1 without know the Dn plus 1? This is contradicts. This is magic here. Okay, how can we do that? So we compare of the three methods we learned here. The general numeric method, right? N plus 1 will becomes this value. And in the incremental method, we use incremental and then calculate the incremental. That in restoring force, we calculate this same result. But M hard definition of M hard for each of them are a little bit different. For the first two, they are the same. Right? The first two, they are the same. But when you're using force, remember M hard are different. You cannot use the same one. Okay, and F hard, you can see using incremental method, becomes shorter. Using F method, you can only calculate the one, and AV also becomes less and less from this one and to this one. Okay. So this is the force space method. So next time we will explain a little bit about nonlinear force. Okay. But we left one part that here that we didn't know how to do the equation to explain how to get F, right? So I will show you another material that is not shown here. I'm showing here. Okay. So I will explain the bilinear model next time, but I will explain how to do the magic in here. Okay. So the order is a little bit changed. So let me do all the lectures in here so that we can save some time in the third time. So we can give you some guideline on the how to do the assignment on the lecture. Okay. So once you know how to calculate the bilinear model, you calculate the bilinear model by each step's force, which is like this one, but I will explain this later. So we will furtherly do a method that based on the incremental of force. Okay, we'll furtherly do an incremental based on force, so that you can see that here is a way that we use force-based equations and using incremental. And we use delta Vn plus 1. And substitute them to n plus 1, that you can get this kind of equation. And then you can get n plus 1 by this one. A very shockingly short, very shockingly less term that you can calculate this. So for the incremental method, remember in the incremental method that we have this kind of equations. But here, using the incremental method, we can somehow predict some force, some displacement. But this displacement is under the case that we pretend the stiffness is not changing. We're using the first stiffness K in here. So that in the first incremental method that we can add this kind of predicted force and divide by the predicted force, linear predicted force here, right? Still, the equation is the same, but we just add some terms here. But we put the term a little bit before, okay? We put K, the D prediction a little bit before them, and put this delta F, which is should be the correct hysteresis force, divided by a predicted delta D based force, multiple the K, okay, which is a linear force. So what this means is that this is the correction of the force. This is the error of the force. Linear prediction and the real force, they have some force error. They have some small difference, right, between linear and nonlinear force. In the real size, that structure will yield, absorb more energy, more deformation, but without the wrong force. Okay, so we just use the delta FC here, which should be corrected, and use the K to predict it here. So that explains the magic of using force. We cannot know the force before loading them. So we can pretend that we know the force by we predict the response by a linear stiffness. So using this equation that we can calculate all the result like this again, okay? But here we get a corrector, which is delta FC. This is only different term that we calculate with the incremental method. Only delta FC are different before the equations. So we using the this kind of separate this part. Others, which when we calculate predictions, we're using this one, but we need a correction term here. And we need a correction term here. So that after corrected, the accurate delta n plus 1 will be the old one, which we're using for prediction force, and minus this term. So this term is the corrector. This is the corrector. This is the predictor part. We predict use linear result, but correct them with nonlinear force. Okay, with this one. So this is a predicted delta A, then this should be corrector. And A, so we say that This is a corrected response, correct response, or say response incremental corrector. Remember that is equals to this one divided by this one. And then we put them, remember we have these two equations, right? Vn plus one, Dn plus one. So that we need to correct this one and correct this term by this corrector, okay? This corrector. Also remember that delta Fn plus one is the correct force, accurate force, incremental force. So we get loading and by bilinear model using predicted displacement. So we get the real force, and then we get the error part of the force, how much error we generated due to the nonlinear force and nonlinear force incremental. And then we calculate the calculator and we correct them by one. So for the velocity, for the acceleration, we just directly correct them by minus this term, okay? Minus this term. This should be minus. And for the velocity, we already predicted one. And then we, using this part to correct them, we use 1 divided by half and delta t, because error is generated in the source of delta A. Same for the d, we also beta delta t square to calculate the correct. Okay. So right now we have a predictor and a corrector method that we can use in the real nonlinear analysis. In the real nonlinear analysis, that firstly we use incremental method to predict AVD with linear stiffness, with the beginning stiffness K. But then we use bilinear model or other nonlinear models to get the real force based on nonlinear models. Now we correct the answer inside the response. Then we get the corrected acceleration. We get correct after corrected response AVD in the correct way. Okay. I think maybe I explained too much. I remember 2 years ago when I had renting this, it cost me about 1.5 hours, but somehow I just explained it in 30 minutes today. So I'm very, very confused. But I'll ask you, have any questions? Well, what is your comment? Too fast, maybe? Maybe too fast? Okay. Or you think it's too easy compared to osmosis detection? Remember before 2 years, I teach this by both Japanese and English. So once I explain in English, I need to explain in Japanese. So it's quite time consuming right now. So it becomes shorter. Okay. No problem. Okay, perfect. So if so, I will continue to teach you about something about bilinear model. Okay. Okay. It should become for the last time, but let's just do it, everything here, okay? Okay, here is what do we get. Later we will know we have the incremental method based prediction and then force based method to correct the result. But we need to learn one more thing about bilinear model. So bilinear model is have a little bit feature here, which is in the beginning, we learn everything based on Hooke's rule, right? So the displacement will be the ratio with the force. You have larger displacement, the force increase linearly, which is in the domain of K1, I showed in this picture. But in the most of the structure, and also soil, and when you pull or press the structure to some point, it will yield. It will yield. It will start to damage. The structure will be changed. So we say this kind of philosophy, effect, this kind of effect as yielding. Okay. This kind of effect of yielding. So steel bar yield when we pull them, and steel structures will be yield when we loading them as horizontal force, and the concrete will be yield if we compress them, right? So after yielding, the stiffness will be changed to a smaller one. Generally, it's a smaller one. So we split them to two parts, which is one part is their elastic status, which is they have the stiffness of K1, and the other status we say they have a plastic status, which they have the stiffness of K2. So after yielding, after yielding, all the force is not depending on displacement only. You're depending on the loading histories. So if you're loading them in different displacement history, then the force will be different. So we call that is a loading history dependency. So changing between this status, elastic and plastic domain, is called yield, which is we call Mark 1, right in here, Mark 1. Mark 1 here. So it's a yielding. So in the yielding, you can becomes K1 to K2. Okay?
Sorry, Sensei, could you share the slide if there is any?
Oh, thank you very much. I didn't share it.
No, I was not sure if you are talking from slide or.
Okay, okay. Thank you very much. Thank you to remind me. Okay, we're talking about this slide. Can you see that?
Yeah, now I can see it.
Okay, thank you. Sorry. So so here is K2, and here is also K2. I draw this figure in both positive and negative side. So in a real earthquake loading, so the loading is not only one side, it's two sides. So they are loaded cyclically to the positive and to the negative. So in the force and displacement domain, you see that there have a point that return back to the other direction. You load into the positive direction, and then suddenly, because of earthquake is a cyclic phenomenon, go and back. It's vibration, right? So you go to some point, and then some point you turn back. Will turn back. The stiffness will not go through K2, but they will go down by K1 because it's unloading effect. Okay, so we can have this kind of experience that you are bending a steel wire, then you have your hands away, then you will keep the shape, right? You keep the shape because the wire is under plastic loading. So the shape they change is the residual displacement due to the loading. So when you dropping down the force to 0 from the top point here, we call this kind of process of unloading. So unloading there and their displacement here to the original point, this distance is their residual displacement caused by loading effect of nonlinear loading of plastic. So this is the work of plastic loading here. We learn it from the static mechanics, but we didn't know how this kind of non-linearity, this kind of plastic loading, do to the dynamic effects, unless we do some experiment or simulation here. So, so theoretically, this kind of loading will using the initial stiffness, as we also observed from a lot of experiments. So once they load unloading, and then they will keep the first stiffness until yield again. Okay, so this is a hysteresis result you will calculate and get from the earthquake. So they will have many this kind of cyclics. So they will be the bilinear model's result, what they look like. So the only problem is how to calculate it and how to use it to calculate structural seismic response. For the bilinear model, we have three parameters: dy, fy, and alpha. Three parameters, and two status: elastic or plastic, and two events: yielding and unloading. So it will be looked very complicated, but later, once you know that the calculation, programming, actually very simple and just a few lines. So let me explain the parameters. Firstly, the yield displacement is when you're loading from zero initial point in the beginning. In the beginning, the point was in zero displacement and zero force, the original point. From the original point, you loading to the positive direction, then you can get your positive yield displacement. And if you load it to the minus direction, you can get minus yield displacement, which should be the same for the most of the time. For the most of the structures, it will be the same. Even for the steel reinforced concrete structures, it's also the same. Positive side and negative side, they have the same yield point. Okay, so the when you're loading to the yield displacement, the force should be the yield force, which is Fy. And their relationship will be linear, and their ratio will be Fy divided by dy, which is K1, which we call the elastic stiffness or the first stiffness. So once you after yielding, the stiffness will change to the second stiffness, or we say plastic stiffness, which is K2. In some of the case, we will show the second to the first stiffness ratio using the parameter alpha, which is we call the stiffness ratio or second stiffness ratio. So in the beginning, where you in the elastic status, so that the range of elastic status is dy1 equals dy and dy2 equals dy minus dy, which is dy1 is the positive side of yielding point, and dy2 is the minus side of yielding point. And we get the dm plus 1 once we get in the positive side, right? In the positive side. Once dm plus 1 is larger than dy1, which is positive side of displacement, then it will be yielding. Or in the other side, dn plus 1 smaller than dy2, okay? In this kind of case. Positive side, you go cross dy1, right? Or negative side, you cross dy2. Then the K, the stiffness right now should change to K2. K also should change to K2. But in the prediction method, we also always use K1, okay, to predict. So make sure that you don't feel confused, which is changing to the second stiffness, okay? This is yielding. So the yielding, there's another condition for yielding, that is that you should in the elastic stiffness status. You should in the elastic status. Okay. So right now K should be equals K1. When K equals K1 and dn plus 1 larger than dy1 or smaller than dy2, then you'll be yielding will happen. So we can change to the plastic status. So when you're in the plastic status, once the loading velocity showing the loading directions, right? Velocity showing the directions of your movement. Once before, last step is positive, next step is negative, then means that you will return and loading happens. And k equals elastic. Again, you change them, k equals elastic again. In this time, you need to update dy1 and dy2. I'll explain how to update them later. So in the negative side, once you are loading in the plastic domain and changing, so Vn was negative in this side, and then suddenly it changes to positive, and then in this step you should know that okay, unloading happened. So we change the stiffness to elastic, and we'll update dy1 and dy2 again, because once you unload it, the residual stiffness will stay, and the plastic working effect will finish. So the residual displacement decided, so that the elastic domain is decided. So how to update the elastic domain? Okay, so when you were loading to the positive and then reducing to the negative, like the figure showing like this, right? The dy1 will become the positive side unloading point. Okay, so it will not, when they cross back here, it will yield again. So this one, so dy1 should become to dn with large steps displacement, and dy2 should becomes that dy1 minus 2 times of dy. So because in the beginning, the positive side is dy, negative side is minus dy, so their range between them is 2 times the dy, right? The range between them is 2 times dy. This range will not change. They shift with unloading, with the plastic loading. So this kind of shift of the elastic domain is called kinematic hardening effect. There are two types of rules, but we basically we use kinematic hardening effect, which is strengthen them the force, but the displacement range of the yielding just a shift with the same amount of the plastic loading. Actually, you can see that it's the same amount. And then we have Vn plus 1 into this side, okay? In this side. In the minus direction, once you unload, then the unload point will be the dy2. dy2 will be dn. And dy1 will be dyn plus 2 times the dy. Still, the yielding range will not change, but they just shift to new place. So we'll summarize the bilinear model like this of 2 status, elastic, 2 plastic status, and 2 event, and yielding and unloading effect, and change them with some conditions. So summarize the event here. If you use using the for the yielding place, right? So that you must have in the status of elastic, and you must keep d in between dy1 and dy2. Okay. Once you go cross over dy1 and dy2, the yielding will happen. Once the yielding happens, we will change the k to k2 plastic. And for the unloading event, that you are must in the plastic status, and the Vn and Vn plus 1 are not in the same direction. So this equations means that they are not used the same direction. So when positive, negative smaller than 1, negative, positive smaller than 0, right? So positive, positive larger than 0, negative, negative larger than 0. So this equation just shows they are in different directions. And then you change once this happened, the status change to elastic, and then uploading them to device 1 and device 2. So how to do the nonlinear simulation is that you will do some calculation to changing the stiffness and calculate the force. But I will explain to you a simple way to do that. Okay. So how to do that is it's like this. This is parameter we have learned. We will explain you another way to understand this. We will split them to two parts. One part is the linear force. The other part is nonlinear force. So once you look at the bilinear model very carefully, you can find that there's a line here, this line here. They can split the whole model to two halves, which is totally symmetric two halves. Okay, so when you're loading, whenever it's linear, elastic, or plastic, they are all loading based on these axles. So if you cut this section, you find that when it's zero, it split the middle of the elastic domain perfectly. This is a minus half, and this is a positive half. Okay, but once you're loading here, when you're loading to this line, they also split the linear and the elastic domain to the two halves. Okay, because they are this gradient is parallel to the second stiffness. Okay, so this also split the elastic domain to two half part. So this point actually is the central point of elastic domain. This part is the central point of elastic domain. So any unloading elastic line across this line will be split to half. The first half will be positive side, negative side. The other half will be the negative side. Okay. So we just using this gradient, we see that by remove this second stiffness, the hysteresis force will becomes like this. They will return to this second degree gradient. So I'll put them down in here. Okay, put them down in here. So that you can see that the second stiffness will become 0. Second stiffness becomes 0. And this stiffness will become K1 minus K2. So that we will split the whole bilinear model to linear part and nonlinear part, which linear part can be calculated always. Whenever D is yield or unyield, this part will all be linear force. Okay, so this force is always be calculated K2D. And for nonlinear part, you need to have a judgment of nonlinearity and linearity, which is first stiffness is K1 minus K2. The second stiffness equals 0. We call this second stiffness is because it becomes a 0. So there's a top limit of the force, which we call this a critical force, QC, which equals to be K1 minus K2 dy. Because this is a gradient of this line K1 minus K2, and this is the yield force for this model, bilinear model, right? So that will be QC equals K1 minus K2 dy. So they are a little bit small than Fy because K1 minus K2 here. Okay. So you can calculate the total force Rn plus 1 by calculate the elastic part and the plastic part and sum them together. So the elastic part is equals to K2 multiple dn, and the plastic part is equals to last times plastic force plus the incremental of this step. Okay. So when the plastic part also in here, right? Plastic here, linear here, sum them together, what becomes the linear part. Okay. But when yielding happened, the elastic part don't change anything. But we say, okay, we calculate the plastic part force like this, but it is larger than QC, right? But actually, it should not larger than QC. So once you calculate the RP larger than QC, we force them to drop down back to QC. Okay, we force them to drop down back to QC, just like RP equals QC, forcefully drop them back. Or they are smaller than minus QC, then we drop back, forcefully equal them to minus QC. By doing this, the bilinear model will be so easy to calculate. Okay. So here is the new rule. Here's the new rule. Here's a new rule, right? Then step by step, every step is go over QC, draw back, go over and draw back, go over and draw back, go over and draw back. By every calculation, do that. Then finally you can get a perfect bilinear model. So for every step, when you code them to programming them, then you use KD multiple K2 multiple dn plus 1 to calculate the elastic part, and you try and error, right? You try to calculate the RP once by RPN and incremental, and then you use the if condition to judge, are they larger than QC? If once they are larger than QC, then put them back to QC. Once they're smaller than minus QC, then place them, equals them to smaller than QC. Then sum the corrected plastic and elastic force together, then you get the real force of here. Okay, so going very smooth. I think today is maybe too much content today for you, and I will finish here. That's actually all the things I need to explain about nonlinearity. So I will upload today's video, both assignment 3 and the lecture video, and also the slide I shared today to the web class, and you can review this contents. Next time, maybe we should do a little bit review work. Okay, so maybe some small test about the equations we explained today. Okay, some small test about the equations. The incremental method, okay, the force-based method, and the predictor and the corrector method, and the bilinear model. Okay. So before next time, so we will have next week, 1 week time, and after that we will do something about assignment 3. Assignment 3 is to do a bilinear model analysis. Assignment 4, right? Assignment 4 will be doing a bilinear model analysis using the method we explained today here. Okay. Okay, so that's all for today. I will finish the Zoom link here. Thank you, somebody, and thank you, everybody.
Thank
If
you.
you have questions, you can stay. Okay.